Alright, this is basically going over the examples for postulates and paragraph proofs. I didn't do example 1 because I thought that was fairly intuitive. I mean, if you actually try to do it, you can probably figure out how many segments you can actually draw from a given amount of points. This one is pretty simple. Determine whether each statement is always, sometimes, or never true. If you need any hints, I would just look at the postulates themselves. For letter A, if A, B, and C lie in plane M, then they're collinear. That's sometimes true. I mean, you can just draw a counterexample for that. I could try to draw one really ugly. Let's try. Here's the plane, and they say that they're collinear, so I can just draw something that obviously is not collinear, like this, and that works. So that's an example of what's called a counterexample. So if you can do a counterexample of something, then that really isn't true. So for all those undefined terms we had, like points, lines, and planes, we really couldn't do any counterexamples for those. So that's why those were accepted as true, even though we couldn't define them. Here in B, there is exactly one plane that contains non-collinear points A, B, and C. Oh, not A, B, and C. Well, P, Q, and R. That is always the case. This one is always. And it's always the case based on the postulate, which I believe is 2.2. I'm going to put here always per postulate 2.2. I'm not going to state it out, but it says it right there. Through any 3 points not on the same line is exactly one plane. So that's done. And non-collinear again basically means 3 points not on the same line. There are at least 2 lines through points M and N. Now that one is definitely never, because with any 2 points you only have exactly one line, and that is per the postulate 2.1. So here we're basically just using deductive reasoning here. This is what we're given. Based on that, we came up with this. Just to give you an example. This is per postulate 2.1. This is per postulate 2.2. This one here, is there a postulate for that? Well, you can actually put here maybe 2.4 if you wanted to. A plane contains at least 3 points not on the same line. If you wanted to. 3 points not on the same line is exactly one plane. You can either do either or, and it should satisfy only because points A, B, and C lie on plane M doesn't necessarily mean they're always collinear. That's what that's saying. So there we just put sometimes for this, because it could happen, but it's not always the case. Don't forget, when you're doing true and false questions, always and never is usually red flags, but that's just, just giving you a tip for that. Alright, the next example I believe was example 3, paragraph proof. Like I said, I'm only going to let you do one. So this one's simple, so I'll go over it. It's in the book too. The given part is like it says, this is the given. M is the midpoint of PQ, and they want us to prove that PM is congruent to MQ. Well, technically, we can kind of cheat here because we know the theorem. We can just say based on the theorem of the midpoint, PM is congruent to MQ because M is the midpoint of PQ. The way the book does it, they just go backwards and they just say since they're equal, then you can say they're congruent. But for me, I'm just going to put here, since this is a paragraph, it means it's informal, so it doesn't have to be exactly in line with what we call sequential. So since M is the midpoint of PQ, there should be a symbol up on PQ, but since I can't put it, I'm just letting you know to say it's a segment. Here I'm going to put point M divides. Well, let's not say divides. Let's say bisects. Since make it easier, point M bisects. And I'm going to put again PQ. There should be a symbol for it. But again, I can't do that. But if you're writing this on paper, you should put the symbol for the segment, which is just a bar on top. Then we can just put here that PM is equal to MQ. And since M is the typo. Since M is the midpoint of PQ, M bisects PQ, thus PM is equal to MQ. And of course, then you can put there furthermore Or, you know, I'll just put since this is just an example, just to give you an idea how it works. Then you can also say since PM segment PM is congruent to segment MQ. Don't forget I forgot to put the symbol. You can also say that I'm gonna write it out. Segment PQ is congruent to, not PQ, what am I saying? PM is congruent to MQ. And here you just put per the definition of congruence, of congruent segments, just to be specifically correct. So here I was basically saying since point M, and since I'm writing this out, I might as well just do it like this. Since point M is the midpoint of segment PQ. Let's just finish this. This is the last example, so we're done. If you understood what I did, you don't have to see this part. I'm just writing it out just to make it look neat. Since the midpoint of segment PQ, point M bisects segment PQ, thus segment, well, I can leave that like that, thus PM is equal to MQ, and since PM is equal to MQ, segment PM is congruent, there we go, is congruent to MQ per the definition of congruent segments. And you're basically done. This is a simple one. So all you're basically saying is since M is the midpoint, you know that PM and MQ are equal because the midpoint by definition divides the segment into two congruent parts or equal parts, and then since they're equal, you can just say that they're congruent because that is a definition of congruent segments. That means the segments have equal length. And that's it for this video. Thank you for watching.